A permutation of the set of positive integers n is equal to 1, 2, all the way to n is a sequence a1, a2, all the way to an, such that each element of n appears precisely one time as a term of the sequence. For example, 3, 5, 1, 2, 4 is a permutation of 5. Let P of n be the number of permutations of n, where k is a perfect square for all k between 1 and n inclusive. And what we want to do is find with proof the smallest n such that P of n is a multiple of 2010. So how do we get started on this problem? It might help to just list out all the integers 1, 2, 3, 4, 5, all the way to n. And then we have some permutation a1, a2, a3, a4, a5, all the way to an, such that the product of 1a1, 2a2, so on and so forth is a perfect square. The natural way to start this problem is to try considering the perfect squares themselves, because perfect squares times perfect squares are perfect squares. And because a perfect square divided by a perfect square is also a perfect square, that means that for each of the perfect square indices, the corresponding permutation part must also be a perfect square. So therefore, all the perfect squares permute to each other. Like 1, 4, 9, 16, etc. Ends up permuting to A1, A4, A9, A16, so on and so forth. And there are floor square and perfect squares. So that means that there are floor square and factorial ways to deal with the perfect squares. But what do we do with the rest of the terms? Well, we have this. Let's consider what happens to the number 2. Then we have a number 2a2 is equal to k squared. And obviously this means that k is even. So we can write this as close to m squared, which is 4m squared. So that means that a2 is equal to 2m squared. In other words, it's twice a perfect square. And because things work nicely with perfect squares, we might want to generalize for numbers that are of the form, suppose 2x squared. Then 2x squared times a of 2x squared is equal to some number k squared, which in turn we must write as 4m squared. And therefore, a2x squared is equal to 2 times m over x squared. So therefore, all of the numbers that are twice a perfect square end up permuting to each other as well. So, and there are square root n over 2 floor numbers of the form 2k squared. And that gives a total of square root n over 2 factorial ways to deal with this. And in general, we have this number 3. If we have the number 3 times k squared, then a3 must also be 3 times k squared. So we also get a factor of n over 3 and then factorial. We might be tempted to think that we can do this for every single integer on the list that we haven't covered yet. But we have to be careful when we hit the number 12, which is 2 squared times 3. At which point, we note that this is 3 times 2 squared, obviously. But we already considered this over here. So how do we exclude all the numbers like 12? In order to do so, we need to ensure that the number that we divide by here is square free, meaning that it is not divisible by a perfect square. If it were divisible by a perfect square, then we could just get rid of that perfect square factor and reduce it to a square free, because the square free deals with the perfect square as we demonstrated here. So therefore, we actually have a specific expression for P of n. We have P of n is equal to floor of root n factorial times square root n over 2 floor factorial times then root n over 3 floor factorial, and so on and so forth, where the denominator goes over all square-free integers that are less than or equal to n. And now we want to find when this is a multiple of 2010. So how do we find out when p of n is a multiple of 2010? Well, it might help to factorize 2010 because it's because each of these numbers are being multiplied. And if there's one factor that we need in each, then we are done. So, and the factorization of 2010 is 2 times 3 times 5 times 67. And this number 67 stands out of the blue. So that means that we want to try focusing on the 67 here. In order to get a factor of 67 in any of these factorials, each one of these numbers has to be at least 67. And because this is less than this and this is less than this, the optimal way to do this is if floor of square root n is equal to 67. And the smallest n that satisfies this is obviously n is equal to 67 squared, which is 4489. So that means that n is greater than or equal to 4489. Otherwise, we wouldn't have that factor of 67. And all that's left to do is that to confirm that this n works. But that's obvious because 2010 divides 67 factorial, obviously, because there's a factor of 2, a factor of 3, and a factor of 5. So therefore, our answer to this problem, the smallest in n that such that p of n is a multiple of 2010, is the number 67 squared is equal to 4,489. And we are done. So thank you so much for watching this video. Please subscribe if you'd like to see more.